Yes.
Thank you very much, Akos. It's a pleasure to be here. So I'm going to tell you about kind of the bulk of my thesis research work, which has been searching for low luminosity, faint high mass X-ray binaries, and what came along with it, which was the study of a large number of sources in a Chandra and NuSTAR survey of the Norma spiral arm. So I want to tell you about why these low luminosity HMXBs are a kind of hidden treasure for us, how we started this search with our Norma arm region Chandra survey, and then followed that up with NuSTAR observations during its first 2 years of the mission. I'll tell you about the diversity of Norma sources that we see and how they compare to the Galactic Center populations where similar Chandra and NuSTAR surveys have been performed. And finally, I'll tell you what our best HMXB low luminosity candidates are and what we're going to keep doing with them. So high mass X-ray binaries are systems where a neutron star or black hole is accreting material from a massive stellar companion. These systems are usually subdivided into different types based on both the type of the compact object and also the spectral type of the massive companion. So we typically subdivide them into OB supergiant systems, which are primarily wind-fed. Accretion happens directly from the stellar wind. And BE systems, where a BE star is a rapidly rotating main sequence B-type star that has a dense equatorial wind. And so these systems tend to be transient. HMXBs are a fairly rare class of objects. So here I'm showing the number of systems that we know in our own galaxy. As you can see, the vast majority of them are BE-type neutron star binaries. And we only know of a very small number of systems that actually harbor black holes in our own galaxy. But although these systems are rare, they're relevant in a variety of astrophysical contexts. They help us to understand the accretion physics onto neutron stars and black holes. And they're the progenitors of neutron star, or black hole systems that will hopefully soon be detected in gravitational waves with advanced LIGO. These systems can also inform our understanding of mass loss from the winds of massive stars and the effect that a binary companion can have on the evolution of these systems. And we now know that most massive stars indeed have a companion. They're even relevant in galaxy evolution. HMXBs can serve as indicators of star formation rate. They may also be important sources of feedback in very low mass galaxies. And in a cosmological context, they may contribute significant amounts of deionizing flux during the epoch of reionization. But why study the faint ones specifically? Obviously, these are the hardest to go after and to study in detail. For one, there's the possibility to discover new types of HMXB behaviors. So over the past decade, the integral satellite has really influenced our understanding of HMXBs. And by basically pushing down the luminosity function of these systems, it's discovered some unusual and interesting things. A subclass of these systems are highly obscured HMXBs, where the absorption that's seen in the X-rays exceeds the interstellar absorption along the line of sight by factors of 10 to hundreds. So here, these systems really allow us to probe the very dense material around some of these HMXBs. Integral also discovered a number of systems known as supergiant fast X-ray transients. These are HMXBs that show extreme flaring behavior, where the luminosity of the system increases by factors of 10 to 100, even 1,000, in just tens of minutes, and these flares last for a few hours. So these are some example light curves of some of these systems. And finally, Integral has really changed our understanding of the relative abundance of supergiant versus BE HMXBs. Prior to Integral, we thought this ratio was roughly 10%, and it's now known to be closer to 50%. Searching for faint HMXBs also has the possibility of discovering the BE black hole population, which has been a question for a very long time. So in the galaxy, we know of about 70 BE HMXBs. 48 of those have confirmed neutron stars, either by pulsations or type 1 bursts. Only one black hole system is known, and this was discovered only last year. In the Magellanic Clouds, we know of about 90 BE HMXBs. 60 of them have confirmed neutron stars. 0 have confirmed black holes. And so it's been a long-standing question whether these systems are just very unlikely to be produced as a matter of binary evolution, or whether for some reason we just haven't been detecting them observationally. And the very first black hole HMXB was discovered just last year, and it was found to have an extremely faint X-ray luminosity. It's in a very quiescent state, and it's only accreting at 10 to the minus 8 of the Eddington rate. And finally, constraining the faint end of the HMXB luminosity function can really help us to understand what happens in these very low accretion states. So what I'm showing here is one of the best measurements of the HMXB luminosity function from integral. And you can see that at the very faint end, there's a possible flattening. With integral, it's only detected at 2 sigma significance. But if this flattening exists, and the degree to which the luminosity function flattens at the faint end is related to both the binary period distribution of these systems and also the presence of a magnetic barrier to accretion, which is thought to play a very important role in neutron star HMXBs at these low accretion rates. So where should we search for these systems is kind of the first question. So here I'm showing a schematic of the spiral arms in the galaxy. The sun is located here. And the red triangles here are known HMXBs. The blue circles are known OB associations. And this particular line of sight that runs tangent to the Norma spiral arm contains both the largest number of known HMXBs and known OB associations. So we decided to perform our search here. And this is kind of showing the actual size of our survey, which covers about a total of a square degree. The Norma spiral arm is also an interesting region to use as a comparison to galactic center surveys that have been performed with Chandra and more recently with NuSTAR. The Norma arm, being in the disk, obviously has a younger stellar population, but it is at a similar distance to the galactic center and suffers from roughly the same amount of absorption, so that making a comparison between these surveys and the sources we see in them is more straightforward. So here I'm showing the mosaic from the Norma arm region Chandra survey in 3 different energy bands. And so the red sources you see here are very nearby soft thermal sources, and the green and cyan sources are those that are more absorbed and very, very hard and likely located in the near or far Norma arm. About 1,000 X-ray sources are detected in this survey above the 3 sigma level, about a few hundred above the 5 sigma level. So what are all of these different sources? One way of getting at that is to look at their distribution as a function of flux. And so the data points here are measured source-flux distribution. And the different colored bands here are predictions based on the luminosity function of CVs and active binaries in blue, of AGN from the Cosmos survey in red, and finally here extrapolating to fainter luminosities, the integral luminosity function are predictions for the number of HMXBs. This is, of course, the big question mark that we want to answer. So this is mostly just to illustrate that, only a very tiny number of the sources in our survey are actually HMXBs. And so we want to, one, understand whether indeed the bulk of this population is CVs, what kinds of CVs they are, and also to figure out how to best pick out the best HMXB candidates. So one way of doing that is spectral analysis, but unfortunately our sources are generally too faint for individual spectral analysis. So we use a technique called quantile analysis developed by Jae-Sup Hong, who's here. And so on the x-axis here is effectively a measure of the median energy. On the y-axis is a measure of sort of the peakiness or flatness, broadness of the spectrum. And the points here are our Chandra sources. And then these contours in red and blue show where a source would fall if it has an absorbed power loss spectrum. And so if it has a photon index of 0, it would lie somewhere here, 1 here, 2 here, and so on. And then sources with very low absorbing hydrogen columns would lie in this part of the diagram, and sources that are very highly absorbed and likely lie in the Norma arm would be way up here. So we split up the sources in this diagram into 5 different regions to get stacked spectra for these different source types. And we find that the sources in this part of the diagram are consistent with being isolated X-ray active stars. The ones here are primarily active binaries, and here we find a population of nearby cataclysmic variables. The sources that are of greatest interest to us lie actually in this part of the diagram. These will be a mixture of AGN and intermediate polars. This is the stack spectrum for this particular group of sources. You can see that in the Chandra band, it's very hard. It has a photon index of 0.6, and it has a very clear iron line at 6.7 keV, which is typically seen in intermediate polars. Any HMXBs that are in our survey, we expect to primarily also lie in this part of the diagram, because we expect them to be associated with the OB associations at about 10 kiloparsecs. Another way of screening which candidates are really our best HMXB candidates is to look for their infrared counterparts. So we searched for infrared counterparts to all the Chandra sources in the VVV survey, and then we targeted the brightest ones to just get a sense for the overall population of X-ray sources, and then the hard ones that lie in that particular region of the quantile diagram. And we got infrared spectra thus far for 52 of these. 20 of them we've analyzed, and 22 more are sort of in our pipeline. And of the 20 that we've identified, 14 have low mass stellar companions. So I'm showing here the H and K band spectra for one of these, and you can see these really nice deep CO absorption features. We've also identified 5 massive stars, and here I'm showing an example of a Wolf-Rayet star in our survey. And we've identified one source that has signatures in the infrared that are more consistent with being an accretion disk. We've since got an optical spectrum to try to understand if we can see the stellar counterpart. And then a couple years ago, NuSTAR started really helping us out in our search for these faint HMXBs, because even if we find a source that's hard in the Chandra band and it has a massive stellar counterpart, we still don't know whether it's more likely to be a high mass X-ray binary or something like a colliding wind binary. So here I'm showing the NuSTAR Norma survey of that same region. Here, as you can see, it's much more patchy than our Chandra coverage, and this is because of 2 significant problems with NuSTAR in terms of background contamination. One is ghost rays, which you can see in this part of the diagram. So a source that's just off, basically, of your pointing, if it's fairly bright, it will create ghost rays in that image. And then over here, you can see an example of another frequent problem with NuSTAR observations, which is stray light. So a bright source that's within 2 or 5 degrees of your pointing can create stray light. And all of these different kind of bite marks that you see in some of this data are where the stray light was basically removed, since we're looking for very faint sources. So in our NuSTAR survey, we detect a total of 38 sources. The majority of them were detected in our NARCS Chandra survey. 5 of them we only detected with NuSTAR for the first time, and we since then have followed them up with Chandra to better constrain their soft X-ray emission. So here what I'm showing is a trial map. So this is a method that JSEB developed and is also applying to the Galactic Center to detect sources, where basically for every pixel, we determine how many random trials would be required to create the number of counts that we see in a circular aperture centered on that pixel. And so again, you can see this is split up in different energy bands, and the sources that appear kind of yellow or white in this image are the ones that are detected above 10 keV. So what are these Norma sources, and how do they compare to the sources we're seeing in the Galactic Center? So there's 3 very bright ones here, which, so this guy over here that caused all those ghost rays in part of our survey is a very well-known black hole low-mass X-ray binary. NuSTAR detected a disk-waned absorption feature, which you can read about in Ashley King's paper. This source over here is a Hess source. It's a very luminous TeV source. And NuSTAR for the first time detected pulsations from the point source at the center of the Hess source. So it's known now to be a pulsar and pulsar wind nebula. This source here is the one known HMXB in our survey that was discovered by Integral. NuSTAR for the first time detects a cyclotron line in this system, so we can now estimate the magnetic field of this source. But what about all of the fainter ones? We've discovered a number of very interesting sources. So one is a potential black hole binary candidate. So here I'm showing the combined Chandra and NuSTAR spectrum, which has a photon index of about 2, which is what you expect for a black hole, but is obviously not super well constrained. However, one of the more interesting things about this source is its variability. So in the NuSTAR band, this is for a single NuSTAR observations, it shows variability that's very reminiscent of a quiescent state of V404 sig, which just recently went into outburst this past summer. And also its long-term behavior, this is from Swift observations, is also very consistent with what we see from black hole binaries. We also detect 3 additional pulsar wind nebula in the survey. 2 of them are associated with known supernova remnants, and this is their spectrum. There are also 2 likely colliding wind binaries. One of these has a Wolf-Rayet counterpart, and the other has a peculiar O-star counterpart that we're still kind of working to better identify. Both of these have prominent iron line features around 6.7 keV and KT temperatures of 2 to 3 keV. The bulk of the sources that we detect with NuSTAR are likely intermediate polars. They have KT temperatures varying between 5 and 20 keV, and 4 of them show iron lines at 6.7 keV with very large equivalent widths. So this is one example of a more nearby source, and this is another example of a more distant source that's more heavily absorbed. But you can see the 6.7 keV line clearly in both of these. And the transients that I mentioned, the ones that we detected with NuSTAR but not in our original Chandra survey, 2 of them are consistent with being flares from non-magnetic CVs, and one instead that's very distant and has a much softer spectrum is probably a magnetar flare. Of the 18 remaining sources that are really very faint and difficult to constrain in terms of their spectrum, half of them have infrared counterparts. Some of these we've observed, and they're all consistent with being low-mass stars. And so these are probably CVs as well, while the other half are most likely AGN, and this is consistent with the number of AGN we'd expect in this survey. So here I'm just showing this time the NuSTAR number flux distribution for our sources in the 3 to 10 keV band. This is what we measure with Chandra in the 2 to 10 keV band, but extrapolated to 3 to 10 using a variety of different models, which in this case all basically lie on top of each other. So this is just showing that the sources we detect with NuSTAR are roughly consistent with what we saw with Chandra. What's more interesting is to actually look at the number flux distribution in the 10 to 20 keV band. At this point, the model that you choose to convert from Chandra to the 10 to 20 keV band makes a big difference. And so you can see that most of our sources kind of lie in between a KT of 10 to 20 or around a gamma of 2. And this is consistent with what we see for individual sources. Comparing this with what Jae-Sup Hong sees in the Galactic Center, most of those sources lie in between KT of 20 and 50 keV. And so it appears that the Norma point sources, the bulk of which are CVs, have lower overall temperatures than the galactic point sources. This could be because CVs in the Galactic Center have higher white dwarf masses than those seen in the disk. Or it could be that in the Galactic Center there's a much larger fraction of intermediate polars versus non-magnetic cataclysmic variables. We do see some evidence for variability in some of our CV sources, and typically IPs are very constant. And so some of our Norma CVs may actually be non-magnetic CVs, which are known to be softer. So what about the best HMXB candidates, since that's what I started with today? So we found 3 HMXB candidates in the NuSTAR and Chandra surveys. 2 of them are Chandra sources that have known BE counterparts, and I'm showing an example of that spectrum here. Pulling up the quantile diagram again, so these two sources basically lie directly on top of each other. They have very high NH. They're likely located in the far Norma arm at a distance of 10 kiloparsecs or so. And they're also very hard, so they have a photon index that's less than 2. And if we assume that distance of 10 kiloparsecs, then their X-ray luminosities are 1 to 2 orders of magnitude higher than we'd expect for isolated BE stars. Our other interesting HMXB candidate has a late B type counterpart. It lies right here, so this is a much more nearby source. It's not nearly as absorbed, but it also has a photon index that's harder than 2. Its luminosity is also about an order of magnitude higher than you'd expect for an isolated star, although for these late type B stars and also for BE stars, the correlation between the bolometric luminosity and the X-ray luminosity is not well constrained, and that's something I'd like to work on in the future. So in terms of using these HMXB candidates to try and constrain the luminosity function, these are the types of constraints that they could provide. So here I'm showing not the luminosity function, but the number flux distribution from that same paper. And this line here shows the predicted number flux distribution for HMXBs. The top line is is without any flattening below a luminosity of 10 to the 34 ergs per second. And this is using the flattening that's seen in the integral data. And so all of our sources would roughly lie somewhere in this box. And so determining exactly which ones are HMXBs and which ones are not should help us to distinguish between some of these models. But of course, we need to actually confirm that these candidates are HMXBs. And so one of the things that we are working on is obtaining RV observations of the infrared and optical counterparts for these sources. And if they are binaries, what we'd really like to do is to measure the compact object mass. The fact that these systems have very low luminosities and that a number of them have BE counterparts makes them interesting candidates for being part of the BE black hole population that was discovered just last year. There are also more interesting HMXB candidates from the NuSTAR Serendipitous survey that's being led by Dave Alexander and Dan Stern. And today, 2 NuSTAR sources with BE counterparts have been discovered as part of this survey, and they both have luminosities that are very low, 10 to the 31 to 10 to the 32. So we also want to target these and obtain RV measurements. Finally, as I mentioned, the correlation between bolometric luminosity and X-ray luminosities for BE type and late B type stars is not currently well constrained. And X-ray surveys of B and BE clusters will help us to constrain that relationship. And therefore, when we find additional candidates that could be interesting BE black holes, we'll have a better understanding of whether their X-ray luminosities are truly in excess of what you'd expect for an isolated system. So to summarize, we found that the dominant populations in the Norma spiral arm are CVs with KT temperatures between about 10 to 20 keV. The Galactic Center CVs appear to have higher temperatures, and this may suggest a difference in the white dwarf masses that are seen in the disk versus the Galactic Center. In the Norma surveys, we found a number of interesting sources for further study, including 3 BBE HMXB low luminosity candidates. And confirming their nature will enable us to extend constraints on the HMXB luminosity function by about 2 orders of magnitude in luminosity. Thank you.
We have time for questions again.
I want to be careful about assigning these all to the Norma arm.
Yes.
Without much better information.
Yes.
Because you're going through the Sagittarius and Carina arm, which have a lot of star formation going on. And I would expect you'd find a lot of sources in there also. Do you see any?
So we don't cross the Carina arm. We cross the Sputum Crux arm, and we cross then the near Norma arm.
It's the same arm, but okay.
Yeah. We cross the near Norma arm and then the far Norma arm. So the reason that at least we think that most of the massive stars we're seeing, if they're significantly absorbed, are likely more associated with the distant Norma arm is because the bulk of the OB associations are there. But I absolutely take your point.
How do we know that there are distant OB associations in the far part of the normal arm? You can't see them optically. There's too much dust.
So I'd have to look at how those surveys were done, but I imagine they were probably in the infrared. Yeah.
Be very careful with those distances. They're
Yeah.
highly suspect.
Yes.
I've been talking with people about the use of the CD population to make up the galactic ridge. And every time I talk to my friends who work in CVs, they warn me that the soft end, the very faint end of the CVs is not well constrained. And extrapolating down to what that population looks like is a very fraught with danger measure. How did you do your extrapolation, and how do you feel about that, the general state of things?
You repeat extrapolation
Of the
what?
CV luminosity function down to the very faint edge, because you were showing what the population looks like down to very faint fluxes.
Right, yeah. So the first thing that I should mention is that that particular work was done, and it includes not just cataclysmic variables, but active binaries. And I think part of the reason for that is precisely because, at least from an X-ray point of view, we can't necessarily we can't distinguish between the two just from the X-rays. And it can be difficult even with the optical counterparts. So that's definitely a caveat there. And from that perspective, I wouldn't necessarily argue that, all of the faint sources that we're seeing that, I plotted in blue or whatever, are actually CVs. There's a good chance that it's some mixture. Yeah.
What is known about the neutron star properties of these new as well as old HMXBs?
What is known about the neutron star properties?
In terms of, let's say, magnetic field of the neutron star?
Yes, interesting question. So for the majority of HMXBs with detected neutron stars that also then have cyclotron line measurements, they're typically in the 10 to 12 Gauss range. There's an interesting sort of subset population of HMXBs that either haven't shown currently any pulsations, or in some cases show very long period pulsations that are like 2 to 5 hours, depending. There's been some talk about whether some of those may actually host magnetars. And then another interesting thing is that one of the models for the supergiant fast X-ray transients, those integral HMXBs that show incredibly extreme variable behavior, one idea behind that variability is that those HMXBs also have neutron stars with very strong magnetic fields, 10 to the 14, 15 Gauss, and that the X-ray flaring behavior is the result of when basically accretion is inhibited or allowed by the magnetosphere. Does that kind of answer your question?
Great. That's okay. That's Francesca.